Okay, then we are ready to start with the lessons. The first one is on the theoretical basic concepts of powder diffraction. And to better understand what is powder X-ray diffraction and also the next lessons after me, I think it's necessary to refresh some fundamental of crystallography. Then we can start with the definition, simple definition of a crystal. What is a crystal? A crystal is a solid in which molecules, ions, or atoms are distributed in the space in a three-dimensional, high-ordered way. And this order is at long range. And with this distribution, we have this, they organize a pattern which is called crystal lattice. Then a crystal lattice, here we have reported two examples, one constituted by parallelepiped and other with only dot points, blue points. A crystal lattice is a mathematical model which the crystallographer uses to imagine, to describe how is inside, how we can describe a crystal inside. And as you can see, it is constituted by a sequence of equivalent points. Each one has the same environment. If you put in a place here and you look around on right, left, up and down, and you move in another point, you see the same. Then they are equivalent in this sense. Then you need to think to the crystal lattice in like something which gives us the possibility to understand how something is repeated. At the moment, when you think of the crystal lattice, not important what we are repeating. It's important the way in which we repeat. This is the crystal lattice because we have another concept which is the basis. The basis is what we repeat, is what we put on each of these points. For example, here I give you a crystal lattice constituted by phases. Then this means that each phase is on each of these lattice points. Then the basis is what we repeat. Okay, but when we know how we repeat and what we repeat, we need also to understand what is the smallest piece that we need to repeat to have the possibility to reconstruct all the crystal at the end, preserving the symmetry and the periodicity. And this is the concept of the unit cell. The unit cell, as we know, is the building block of a crystal, is the smallest volume that we repeat in the space, only translated it because the symmetry, the periodicity is already inside the unit cell. Then you take the cell, you only translate in 3D, and you recover all the crystal lattice. Here an example of how we can choose this unit cell. We have many. These two, for example, because the lattice points are always at the corner of your unit cell, these are an example where they have only crystal lattice at the corner. But as we will see later, we can also choose different unit cells having more lattice point, not only at the corner, but we will see this. In addition, in the unit cell, we can have more atoms or more molecules. For example, the quartz contains 3 molecules inside of the unit cell of CO2. Then the crystal structure, to summarize, consists of identical unit cell, which contains each the same arrangement of atoms, this one, which is translated in the space to give us the final, our crystal. Okay, then we have understood how we can repeat something, what we repeat, and what is the minimal volume that we can repeat. But have we an infinite way to translate this unit cell or not? No, we have a limited number of ways with a unit cell can be translated in the space to fill completely the space without leaving some void, some gap. And the way in which we can do this is called crystal system. In 3D, we have 7 crystal systems, which represents the 7 way in which a unit cell can be translated in the space. A unit cell is characterized by the so-called cell parameters. We have 6 cell parameters. They are A, B, C, which are the lengths of the parallelepiped, and the corresponding angles between them. Okay, what are these 7 crystal systems, or what are these 7 ways with which we can translate the unit cell in the space? They are this one, all of us know this. We have triclinic, monoclinic, hexagonal, trigonal, orthorhombic, tetragonal, and cubic. And they are defined by the relationship that exists between ABC and alpha, beta, gamma. You can say here that each crystal system has a specific and unique relationship between ABC and alpha, beta, gamma. If you are in a cubic crystal system, A must be equal to B, must equal to C, and alpha must be equal to beta, to gamma, and equal to 90 degrees. In this case, then, we can say that the crystal system defines the shape of your cell. You can see how this change. And while the crystal lattice describes the size of your cell. In this case, we have cells where the lattice points are only at the corner, as I said before, and they are indicated with the P letter, and they are so-called primitive cells. But we can have different cells for not all the crystal system, but for some of them. For example, for cubic, tetragonal, and orthorhombic, we can have also I cells or F cells, or for monoclinic C cells. What they are? They are called body-centered, face-centered, and C-centered. This means that in this case, in addition to the lattice point to the corner, you have one more lattice point inside at the center of your parallelepiped. Here you have all the faces having one lattice point. And here you have at the opposite face the lattice points. Then at the end we have 4 types of cells, this one, that combined with the 7 crystal system gives us the 14 Bravais lattices. Okay, but let's go on. I have given you all of this information, but I think that another important aspect to consider to study and understand crystal is also to consider where we are in the crystal. What are the direction in which we are moving? Because more of the physical properties of crystals depends on this, depends on the direction. For example, here there is a graphite structure. This is the crystal, this is the structure. And for example, the electrical conductivity in graphite is very different if you are moving along the plane or perpendicular to them. And at the same way, for example, mechanical stress depends on the direction in which you are applying the stress, and the material responds in a different way. Okay, then the direction is an important key to understand and to study, and also to predict the crystal's properties. And to to issue this aspect, we introduce a new concept, which are the lattice planes. The lattice planes are a set of parallel planes which contains many lattice points and are used just for this, to visualize how the atoms are oriented and arranged in the solid. We use the so-called Miller indices that you know, HKL, to describe each lattice plane. Here there are shown 3 examples of lattice plane. You can see that they are indicated with round bracket. Inside we put the HKL value. This is the lattice plane 100, this is 110, and this is 111. Why? Because as you can see here, HKL is equal to the reciprocal of the intercept of the plane with ABC. In this case, for example, the plane intercept in a position X only A, while it is parallel to B and C. Because it's parallel, the intercept is infinite, then the reciprocal on infinite is 0. This is the reason why it is 100. And in this way, you can apply to have the Miller indices of all the plane. But we can go on of this, and we can say that starting from one plane that you have defined, this red one, that is light blue or green, you generate with the same Miller indices all the parallel plane to obtain the so-called family of plane. The family of plane is given or represented by a curly bracket, and inside also we put HKL. We can see here that the parallel planes have a distance, are all equivalent, parallel, at a specific distance, which is T. We have a distance for this red, another distance for the green, another for this violet. And we can see that when the Miller indices increases, for example, moving from this family to this or this, this spacing decreases, you can see, moving from here to here and here, and also the number of lattice points in the family decreases. Okay, why I am speaking about T? T is important because, as we will see, it is an important quantity that is in the Bragg's law, which is a fundamental law to describe the diffraction. And another important thing is that T is largely used in crystallography because it depends only on the crystal, on your crystal, not in which way you are making the measure, your diffractometer, your experimental condition. It depends only on the crystals. In fact, for each crystal system, we have an expression of D, and you can see that for each crystal system, it is related or depends only on A, B, C, alpha, beta, gamma, and the 3 Miller indices corresponding to the family of plane that have given you the diffraction effect. Okay, I have given you really the few elements of crystallography to try to better understand what follow now. Now then, because our goal is to speak about the powder X-ray diffraction, we can define what is the when the diffraction occurs. The diffraction occurs when an incident wave is scattered by a periodic array with a long range order, and the diffracted beams is able to produce a constructive interference at specific angle. Then, if this is a simple definition of diffraction, why crystals are able to do this? They are able because, as you remember, also the crystal is, for definition, a periodic distribution at long range of atoms or molecules. Then the crystals satisfy completely this condition, and then this is the reason why a crystal is able to perform a diffraction. Additionally, why we use X-ray specifically? Because the X-rays has a wavelength in the range of 0.1 to 10 angstrom, which is exactly the distance between the atom inside the crystal, and then X-ray looks at the atoms in the crystal exactly as a periodic array, and then the atoms can act as a coherent point scattering, giving us a diffraction effect. And the diffraction effect in crystallography, we call this as a diffraction pattern, which contain all the information about the crystal, and then we can use the diffraction effect to study our crystal. A completely different situation, we will see better, is represented by the amorphous. What are the amorphous? Amorphous is some materials where we can, for example, maybe we don't have completely periodic distribution of atoms inside, or we can have irregularity, but not a long range, only at short range. And in this case, for X-ray, they are able to diffract them, but they are not able to give us a diffraction pattern constituted by peaks, but only diffuse scattering, a bump that I will show you. Okay, for which we can use X-ray? X-ray diffraction can be used to study single crystal, which are generally crystallite with this dimension between 200 to 300 micrometers, or for powders. In case of powder, they are very small crystallites with the dimension ranging from 1 to 5 micrometers. Okay, but if we have a crystal, single crystal of powder, and we illuminate this with the X-ray, they are always in the condition to diffract and to perform a diffraction? The answer is no, because there is a very important law, which is the Bragg's law, which gives us a simple model to understand what are the conditions that the crystal needs to satisfy to perform a diffraction, to give a signal that can be recorded by the detector. The Bragg law, that I am sure all of you know, is this one, is 2d of HKL sin theta equal to n lambda. What it means? It means that if we have, for example, a set of plane like this, obviously, as I said, they are characterized by specific distances, okay? This is this DHKL about I spoken before. Okay, in this case, the incoming beam arrives at, we suppose, a theta angle, and it is diffracted at the same theta angle. Okay, when all of these diffracted beams, these all diffracted beams, when they are in a coherent condition, they can give us a diffraction effect. But this happens only when the Bragg's law is satisfied. Only when the family of plane is respect to the incoming beam at a specific 2 theta angle, which is given by the Bragg's law. And because we know that lambda generally is a constant, because if you, for example, perform the measure at the laboratory at home, you have only one lambda from your diffractometer, then lambda is a constant. Also, D is a constant, because if we are looking at a family of plane, this family is characterized by a specific D value. Then in this formula, all is constant except theta. Then I repeat, theta is the angle or the orientation of your plane, which must be satisfied law to say the Bragg condition, and then to give you diffracted beam that constructively interfere, and then give you a resulting signal that can be collected by the diffractometer and give you what we want, your signal. Okay? Then we can associate, if we collect a diffraction pattern like this, we can assign to each peak the corresponding set of plane from which each peak generates. Okay, then, but when I collect this signal, what is important? What we need to look from this? I have a peak. What is important? To study a crystal, we will see with the application of X-ray diffraction, very important are the position of your peak and the intensity. Why the intensity is so important? The intensity is the integrated intensity, which is the area under your peak that you can measure when you perform a diffraction experiment. It's important because it is related to the modulus square of the modulus of the structure factor, this new quantity, f of HKL. The structure factor is a complex quantity given by this formula. This means you can see that there is a summation over all the atoms in the unit cell. Then this means that to this specific intensity, all the atoms in the family of plane characterized by these HKL values contribute to give the intensity. But it's important that we put your attention on these two quantities, Fj, which is the scattering factors, and XYZ, which are the fractional coordinates of the intensities of the atoms, in the unit cell. Why? Because we can say that the intensity that we measure is determined by how the atoms are distributed in the unit cell. Is because we have this quantity here. And because the position of the atoms are in F, because F is related to I, and because I is what I measure, this is the reason why I can recover the structural position and to solve our structure at the end when we perform a structure solution by powder. But it depends also by Fj, which is, as I said, the scattering factor. The scattering factor here represented quantify the efficiency with which each atom is able to scatter an incoming X-ray. The distribution is this one. You can see that we have a different curve for each type of type of atoms respect to theta, and the ability, the efficiency is maximum at 0 angle, and it corresponds exactly to the number of electrons inside the atoms, and it decreases while we move from 0 to higher theta angle. Why? Because when we move from 0 to higher theta angle, we start to measure, or we start to find destructive interference. At theta, we have completely constructive interference that we collect the maximum signal. Moving, because here we are exactly at Brad's condition, that we fully, completely the Brad's law, and then we collect the maximum signal. Then we move with theta, and then the destructive interference increase, and then the signal given by your crystals decreases. Okay, but let's go on just a little bit to say that obviously all of us knows that the crystal is something real. We can look, it exists in our space, which we call real space, or in crystallography also direct space. But what we collect when we perform a diffraction experiment on the crystal, are you able to see directly the crystal again? No. No, why? Because the X-rays cannot be focused in the same way, for example, that ordinary light. Our eyes are able to focus the light coming from an object, and then we can reconstruct the image and see immediately, directly, this image. This is not the same in case of X-ray, because we don't have some lens able to do this. And then what we collect is an image of our crystal, not in the real space, not in our space, but in the reciprocal space. Fortunately, obviously, the reciprocal space is not a physical space, it's only a mathematical construct, but because we have a mathematical relationship between the real and reciprocal space, we can go from one space to the other, and then even if after the measure we are in the reciprocal space, we have tools to reconstruct and to see our crystal in the real space. Okay, to better understand, I show you the case of single crystal. In case of single crystal, we have here a single crystal, the sample, X-ray incoming, and the diffracted effects are collected by a 2T detector. What we collect is this one. This is the reciprocal space that I spoken before. It is constituted by a lot of spots. In fact, we can call this spot pattern. And in case of single crystal, we have an orientation of the crystal respect to the incoming beam. And this is important to take in mind, to your mind, because we will see the difference respect to powder. We have, in case of single crystal, only one direction of scattering, which gives us this point. Why this? Then here you can see that if you have one orientation of the real space, you have also one orientation of the reciprocal. Why this is important? This is important because in case of single crystal, you can have access to the three-dimensional space, and then you can measure exactly the intensity of each spot that you can use to solve your structure, for example, by using direct methods, I don't know. And this is important because you don't do any errors when you measure the intensity of this spot, because they are accessible in 3D. This because we have only one direction in case of single crystal. Okay, what happened at the contrary in case of powder? The situation is completely different. I will show you. And making the structural characterization of powder really a problem, challenging. But we work on this. First of all, I want to say, obviously, the definition of powder. What is an ideal powder? This is a definition of an ideal powder. An ideal powder is constituted by an infinite number of randomly oriented crystallites, all with the same size, all with same type. Then the powder ideally is pure, not a mixture, for example. In practice, we don't have a lot of this aspect, in the sense that we have already a finite number of crystallites. We can have that also the randomicity can be not satisfied completely from all the crystallites inside the powder, and they can have also different dimensions. But we study, we suppose that we are working with ideal powder. And why we use powder? We use powder because, I want to say that if you have a single crystal like this with good quality and right dimension to perform a single crystal diffraction experiment, than to study your crystal as a single crystal, it's better that you do this instead of powder. Okay, then if you have a single crystal, you study with single crystal, but not always it's possible to have single crystal of sufficient size and or quality to perform a right single crystal diffraction experiment studies. And sometimes, for example, when you speak, for example, about pharmaceutical compounds, they crystallize as powders. Then also in that case, the only possibility that you have to study your compounds is as a powder. But I want to show you also that even we have many problems with powder, all the information of your compound is inside the diffraction path. And I will show you that it is difficult, but all the information is there. The difficulty is to recover this information in a correct way or in some way, but it's there. Okay, in which way the diffraction is in case of powders? We said that the powders is constituted by a randomly oriented high number of crystallites. You can think to each of these as a very little single crystal, okay? Then the diffraction arrives on this, and instead of a single crystal where we said we have only one direction of diffraction, because we have here now that many crystallites are simultaneously satisfying the Bragg's law, all of these are able to simultaneously perform the diffraction effect. And the diffraction is, in case of powder, in all directions, okay? Not in one direction, in all directions, giving origin to these cones, which are called the Bari cones. And each cone corresponds to a family of plane from which the cones originates, and they correspond to a specific 2 theta angles, satisfying the Bragg's law. Then when the detector scans the samples, it intersects the cones and give you the signal that you collect, which is what we know. All of you, if we work with powder, know what is the result. The result is this one, a diffraction pattern constituted by C-paired peaks. But what the problem? The problem is that in case of powder, as I said, to each peak, we have not only one contribution coming, only one reflection. We have the contribution coming from all reflections that are at the same 2 theta angle that in that moment satisfy, I repeat, the Bragg's law. Then instead of single crystal, where I said we collect a spot pattern, and we can measure with accuracy the intensity of these, each of these spots, this is not the same here. This is not the same here because to measure correctly the intensity is not possible because we have this big problem unavoidable in case of powder, which is the overlapping, okay, of reflection. And then, what are the problems that we have and make difficult to characterize or study a diffraction signal, a diffraction data? First of all, as I said, the overlapping. You can see here better. Here I have a part of your diffraction pattern, no? Then we see we have collected only 2 peaks. Then we have access to these only 2 peaks, but under these two peaks, we have the contribution coming from 5 reflections, okay? And to characterize the compound, we need to assign the corresponding intensity to each of these reflections as well as correct as we can. But additionally to the overlap, we have, in case of powder, also the problem to correctly estimate the background, for example, above all at high to theta angle. Why? Because at a high angle, the signal reduces, the peaks enlarge, and then it's difficult to correctly distinguish between signal and noise. Then in case of powder, you generally make mistakes, or it's easy that you make mistakes in the correct determination of background. Also, as I said, powder is ideal. Powder is constituted by randomly oriented crystallites, but in many cases in real crystals, we have in many cases we have that a part of these crystallites prefer a direction. They are aligned in one direction, not randomly oriented, okay? And then, as a result of the diffraction, we collect some very intense peaks, okay? And these modify the relation between the peaks inside of your pattern. Another problem can be the presence of the amorphous. As I said, the amorphous component gives a scattering diffraction and a bump in your diffraction pattern. And all of these problems for sure don't give you the possibility to collect really correct the position or intensity that you need to study. But there are ways that my colleagues in the following lessons will explain you. Okay, then we have understood that it's important to try to make the minimum error when we try to calculate the position of a peak or its integrated intensities. For example, then what we do? In this case, for example, if we have this collected, observed diffraction effect, and I want to calculate what is the profile intensity calculated at this point, I use this formula that Paolo will explain better in his lesson. This is the formula. We have a scale, we have a summation overall the contribution to that point, and in the intensity we have the multiplicity. This factor is the Lorentzian correction. This is, we know, the modulus of the structure factor, and we have also the functions describing this one, the shape of your peak, this the asymmetry, and also we have the contribution coming from the background. Obviously, because of the problem that I said, we need to perform profile fitting to refine some quantities, a profile fitting procedure, which is based on least square. And in this case, the idea is to minimize, obviously, the differences between calculated and observed profile. Some information about what we use to describe the background. Generally, it is described by using a polynomial. For shape function, we use different function also. We can use Gaussian, Laurentian, pseudo-void. For the fluid at half maximum of your peak, use also some functions which depends on 2 theta, for example, the Cagliotti formula that I suppose you know. And during the profile fitting, what we minimize, what we refine. Obviously, we refine the 6 cell parameters, the 2 theta 0, the background, the fluid, the asymmetry, and so on. But to conclude, I hope that you have starting to understand how difficult can be to manage diffraction data to obtain what you want. But in this slide, I report some of the application. You can see that they are a lot. This means that even if it's difficult, we have the possibility to manage the data to obtain what we want, because I repeat, the information is there. Then we, for example, can use diffraction, powder X-ray diffraction for qualitative analysis, Aurelia will speak about today, to define how many phases are in your sample, if it's pure, or if it's a mixture, how many. Okay, or you can use for quantitative analysis, then to quantify how much of each phase is inside. Or this, for example, to do what is my job, to characterize, to obtain the final model, in powder, to obtain the so-called crystal structure, then to know where the atoms are inside the unit cell, you need to follow a sequence of steps starting from the unit cell parameter determination, followed by the space group determination, the decomposition of the experimental powder diffraction, then followed by the application of methods that give you the final model, for example, direct method or simulated annealing, it depends. And to end with the Rietveld to refine it and obtain the final crystal structure. Or we can use for all of these, for example, to study the texture. When I said we don't have the randomly orientation, but we have the preferred orientation, or if we want to evaluate some strain which is remained in your crystal after some process, thermal or mechanical, I don't know. Or if you want to detect some lattice, small lattice distortion, which are caused by defect or stress. Then, okay, we have understood that we can. We will understand better with the next lessons in which way. I want to conclude with this slide to convince you completely that we can do this, because I show you here 3 diffraction, powder X-ray diffraction pattern, one from cristobalite, the other from quartz, and the third from CO2 glass. They are constituted by the same identical element, CO2. They are equal in this case, no differences for this, okay? But we collect 3 completely different diffraction pattern. 2 of these with peaks, because cristobalite and quartz are crystal, and then they have as I said, this periodic distribution of atoms, and then they are able to produce a diffraction effect constituted by peaks. While this is amorphous, and as I said, the diffraction is a diffuse scattering, then we have no peaks, but this bump, okay, in the diffraction pattern. Why we have this difference? Because even if they are constituted by the same element, silicon and oxygen, you can see here that they have a completely different structure, okay? And because the X-ray powder diffraction pattern is a fingerprint of your crystal, from there you can obtain and reconstruct all the information that you need about that specific crystal. Okay, thank you.